Welcome to Mass Transfer Operations lecture series.
In the last lecture, we discussed mass transfer in stage-wise contact of two phases. We also discussed a graphical method to determine the number of stages. So everyone is familiar with the notations used here. In today's lecture, we will try to discuss a, an algebraic method for the determination of number of ideal stages. So here both operating and equilibrium line should be straight. Then only we can use this method to find the number of stages. So this is the basic representation of a tray tower with a few trays shown at the beginning, at the end, and two trays in between. To solve this, I'll consider two envelopes. One envelope is from the first tray to the nth tray, and I'll also consider another envelope with that covering the whole of the tray tower. So let us try to write the solute balance for the first envelope, that is solute balance from the first tray to the nth tray. So here the gas, even when I consider this envelope, the gas is entering from the nth tray, it is leaving from the first tray. Liquid is entering from the first tray and it is leaving in the nth tray. So let's write the solute balance. Rate n is equal to rate out. Gs into yn plus 1 plus ls into x0. That is the rate at which solute is entering. Here Gs into yn plus 1 plus ls into x0. Similarly, solute leaving is equal to Gs into y1 plus ls into xn. Gs into y1 plus ls into xn. So we can rearrange and get yn plus 1 minus yn is equal to ls by gs into xn minus x0. So if I consider the whole of the tray, so this inlet and outlet changes, and I can similarly write yn plus 1 minus y1 is equal to ls by gs into xn minus x0. And also I said that this method is possible only if the operating line and equilibrium lines are linear. So this is a graph between x and y, where x is the mole ratio of solute in liquid phase, y is the mole ratio of solute in gas phase. So the representative diagram give you the operative line, operating line and the equilibrium curve. Since we have assumed both to be same, so this is the equilibrium curve and this is the operating line. You can see operating line is found by connecting the 2 points x0 y1 and xn yn plus 1. See, x0 y1 and yxn yn plus 1. So I hope it is clear till now. And we already discussed the graphical method, how to construct the steps and all. So this is we can count 1 2 3 4 5 6 stages or 6 plates. So here this is xn plus yn plus, that is the concentration of liquid solute in liquid phase leaving the nth tray, and the concentration of solute in gas phase entering the nth tray. So if I draw a vertical line downwards, it will meet the equilibrium curve. So the points in the equilibrium curve, that is xn comma yn, actually represent the equilibrium concentrations in the nth tray. So if I take the nth tray here, any point on the equilibrium curve will be the corresponding equilibrium concentrations in that nth tray. So if you take this point, this will give you the equilibrium concentrations in the n minus 1th tray. So on and so forth this goes. Okay, now we already discussed the relationship between for the equilibrium curve. Y is a function of x. Here y is mole ratio. So here y is mole fraction of solute in gas phase and x is mole fraction in liquid phase. So similarly, I can write y is equal to alpha into x, that is relation of mole ratios in gas phase and liquid phase. In this case, this means alpha is the slope of the equilibrium curve, and here it is a line. Okay, now since all the points lies in this curve, like equilibrium curve, I can write yn is equal to alpha into xn. Here yn is the equilibrium concentration existing in the nth tray. Xn is the equilibrium concentration existing in the liquid phase of the nth tray. So let's substitute 3 in 1 this equation. Now I'm going to discuss the procedure to find the uh, number of trays. So you will have to understand it in this particular way. We'll follow a particular procedure. So here yn plus 1, so I can like what I'm going to do is I'm going to substitute this y is equal to alpha into xn in this equation. So I'll get yn plus 1 minus y1 is equal to ls by gs into yn by alpha minus x0. From this equation I can write xn is equal to yn by alpha. So xn is equal to yn by alpha. Okay, now I'm going to introduce another term, a bar. So before that, let us try to multiply this inside. So we'll get yn plus 1 minus y1 is equal to ls by alpha gs into yn minus alpha into x0. So let's multiply. So I can write, I'm going to call this term ls by alpha into gs as a bar. It is called absorption factor. So let's see what it is. Here we will try to simplify a little bit more. Yn plus 1 minus yn plus 1 minus y1 is equal to a bar into yn minus a bar into alpha x0. So we can rearrange this like this: yn plus 1 minus a bar into yn is equal to y1 minus a bar into alpha x0. So I am going to call this as equation number 4. So here a bar is equal to ls by alpha gs is known as absorption factor. So what is absorption factor? It is a ratio of slope of operating line to the slope of equilibrium line. We know that ls by gs is the slope of operating line and alpha is the slope of equilibrium line. So the ratio of these two can be called as the absorption factor, and it is represented as a bar. So now onwards you need to consider this equation number 4 to solve further. So this equation number 4 is a non-homogeneous difference equation, because this is actually the difference of two consecutive values of y mole ratio, the values of y in two adjacent trays. So that is why we call it as a difference equation, and it is non-homogeneous because the RHS of this equation is not equal to 0. So we will try to solve this. We need to find yn plus 1, yn ln. So let's try to solve this, but we'll adopt a particular procedure. We'll make some assumptions and we'll try to solve this. So here, the first we'll try to make this solution homogeneous by assuming the RHS to be equal to 0. This is a method to find the solution. You have to learn as such. So I can write why I'm assuming it yn plus 1 minus a bar yn is equal to 0. If this is the case, I can again assume a solution for yn. So yn is equal to k1 into z raised to n. I do not know what is k1, I do not know what is z, I do not know what is the value of. So I'll try to develop a method to find all these. Now substitute 6 in 5. I can write k1 into z raised to n plus 1, because if when yn is equal to k1 into z raised to n, yn plus 1 will be k1 into z raised to n plus 1. Just replace n by n plus 1. That's it. Minus a bar into k1 into z raised to n is equal to 0. Solving this, I get z is equal to a bar, the absorption factor. Now, so based on this assumption we got z is equal to a bar. I'm going to assume another particular solution. Yn is equal to k2, a constant. Here I assume yn is as a function of n. And there is another possibility. Yn can also be a constant. That is also possible. Then both yn plus 1 and yn will be equal. That is also another possible solution. So in that case, and let's try to solve this. But then we cannot use this equation, but we have to use the non-homogeneous difference equation. Let's apply this in the equation, the assumption yn is a constant in the equation number 4. So for that, let's assume a particular solution. Substitute 8 in 4, the equation number 8 in 4. I can write k2 minus a bar into k2 is equal to y1 minus a bar alpha x0. So where is equation number 4? See, in case of yn plus 1, write at k2 minus a bar into k2 is equal to y1 minus a bar alpha x0. Okay, solving I get k2 is equal to y1 minus a bar into alpha x0 by 1 minus a bar. Okay, now we had two different solutions for yn. Yn we assumed that yn is equal to k1 into z1. I have assumed yn is equal to k2. Let's combine these two and write the general solution for the equation number 4. That is yn is equal to k1 into z raised to n plus k2. So we know what is k1 and what is k2. So let's try to substitute that. So I can write y1 is equal to yn is equal to k1 a bar raised to n plus the value of k2 y1 minus a bar alpha x0 by 1 minus a bar. Now we have to find k1. So we know a relation between yn and xn. Yn is equal to alpha x0. Substitute for n is equal to 0. I can write y0 is equal to alpha x0. Here y0 is equal to let's try to put n is equal to 0 in equation number 10. So I can write y0 is equal to k1, n is equal to 0. So this terms becomes equal to 1 plus y1 minus a bar alpha x0 by 1 minus a bar. And we know y0 is equal to alpha into x0. So write alpha x0 is equal to RHS. And from solve this and we'll get k1 is equal to alpha x0 minus y1 by 1 minus a bar. So now we go to the values for all the terms, all the constant. We go to what we know what is k1, we know what is k2, we know what is z. So let's write y1. So let's substitute 11 in equation number 10 and write y1 is equal to alpha into x0 minus y1 by 1 minus a bar into a bar raised to n plus y1 minus a bar alpha x0 by 1 minus a bar. So we got the value concentration yn, that is the equilibrium concentration in the nth plate. So now let's try to determine the total number of plates, capital N, because that is what we need. So if we know y1, yn we can replace n small n by capital N, and we can write the determine yn plus 1. If I want to know n plus yn plus 1, wherever there is n, replace n by capital N plus 1. So I can write yn plus 1 is equal to alpha x0 minus y1 by 1 minus a bar into a bar raised to n plus 1 plus y1 minus a bar alpha x0 by 1 minus a bar. So if you rearrange this equation, I can write this equation into this form. A bar raised to n is equal to yn plus 1 into 1 by a bar minus 1 minus yn by a bar minus alpha x0 by alpha x0 minus 1. So you need not show the detailed rearranging steps. Just write that just find this expression up to equation number 12 and you can write rearranging, you get a bar n. But we need to find n, the total number of ideal states. For that we can further rearrange and we can take logarithm on both sides, and simplifying I get n is equal to this equation log yn plus 1 minus alpha x0 by yn minus alpha x0 into 1 minus 1 by a bar plus 1 by a bar. So the above equation is known as Kemp's equation. Here we know everything. All the quantities in equation number 14 are known. Yn plus 1 the concentration of solute in the gas phase entering, x0 the concentration of solute in liquid phase entering, y1 concentration of solute in gas phase leaving, a bar the absorption factor, which is the ratio of equilibrium line and the operating line. So by theoretical calculation we can find the total number of trays. But the solution method that we used can be is applicable only when is not applicable when a bar is equal to 1. That is when the slope of operating line and equilibrium line are equal. So I can rearrange equation number 4 when a bar is equal to 1. So equation number 4 becomes yn plus 1 minus yn is equal to y1 minus alpha x0. Now we can let's call this as equation number 15. Write the equation number 15 for n is equal to capital N minus 1, n minus 2, etc. That means replace n by capital n minus 1, n minus 2, etc. So we will get a set of equations, and if you add all these equations you will get y capital N plus 1 minus y1 is equal to n into y1 minus a bar alpha x. So rearranging n is equal to yn plus 1 minus y1 by y1 minus a bar alpha x0. This will be the value of number of trays when a bar is equal to 1, the case in which equilibrium line and operating lines are parallel. Okay, so you can also refer to the um, algebraic theoretical equation for number of stages in case of stripping, that is the process in which the transfer of fluid takes place from liquid phase to gas phase. Equation is like this. Here there is a term 1 by a bar known as s bar is known as is the inverse of absorption factor, which is called stripping factor. Okay, I need to discuss one more topic, that is minimum liquid rate for absorption. This is absorption, please don't confuse. Here slope of, so you can see this is the operating line, this is the equilibrium curve. It need not be a straight line always. So the slope of the operating line changes as the line moves towards the equilibrium curve. So you can see that the equilibrium slope is Ls by Gs. So the minimum, when the slope decreases, that means the value of Ls is decreasing. Here the liquid rate, the minimum liquid rate is defined as the case in which the line PQ double prime is the tangent to the equilibrium curve. The liquid rate for which the line PQ double prime is tangent to the equilibrium curve will give you the minimum liquid rate, because we can operate the rate over at different rates. The minimum possible liquid rate happens when the operating line acts as a tangent for the equilibrium curve. We will solve a problem based on this.